Check. 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 Okay, let's go ahead and begin. So, I was just speaking to the instructor of the econ class right before us, and they're having a midterm this week also. And guess what day it is? Friday, of course. So, I just want everybody to be aware of that. So we have tentatively decided that at least one step that we're going to try to do to avoid a traffic jam and a collision is have her class exit that door and our class enter that door. That having been said, there's 15 minutes between classes. I don't want anybody entering more than 7.5 minutes before class. So that would be 12 minutes, 30 seconds after the hour, 1:12, 30 seconds. Am I right? Yeah, they end at 05. Halfway between is 12 minutes and 30 seconds, and then we start at 20 after. Okay, so at least give them all of that, their half, to get out. So don't start filing in here and claiming a spot while they're still in here trying to put their papers together and leave. Okay? You come in this door, they leave through that door. Now I've got to talk to the next instructor and find out if the guy after us is also having a midterm. That's possible too. So, but we'll deal with that if it comes up. All right, so that's the midterm. You notice that there are midterm, okay, the date of the midterm. It's the full class period, 1:20 to 2:25. Okay, hour and 5 minutes. You can expect something on the order of 5 or 6 problems, 7 at the absolute outside. Those would be short problems. Maybe 5 problems if some of them were multi-part. I did post some review problems. Not all of these problems are necessarily in force. It depends on how far we get by end of business on Wednesday. But much of what we have here, for instance, this problem, I think, is a homework problem for Wednesday. This is something I did in class. And I warned you that I often put that particular problem on midterms. So, when I say something like that in class, you should write that down and say, remember that problem or remember that solution. Here's another thing you should remember. Stirling's formula. Am I going to give you Stirling's formula like I did here? No. I mean, the statements of these problems are probably a little briefer than you would see on the exam. So when you're taking a beginning algebra class, do you have to memorize the quadratic formula? Yes. When you're in this class, you have to memorize Stirling's formula. Okay? And be able to use it and the algebraic simplification that it provides in order to prove things like this and this. Okay? What else? Some algorithms. Most of this stuff you can do. What you can't do yet is all the stuff that depends on induction. So we'll try to get to that today and Wednesday. I doubt we'll get to the material needed for problem 19, but I'll let you know if we got that far by end of business on Wednesday. Okay, so, yes, go ahead. The summation formulas. You mean like sum of I is n times n plus 1 over 2. I wouldn't have thought it necessary to say it, but yeah, you should know that. What about the sum of the squares? Well, you know what? I think it should be part of everybody's mathematical heritage that they know at least the sum of I squared, and the sum of I cubed. Right? If you forget sum of I to the power 4, That's not a big deal. Am I going to use those? Am I going to require those? I seriously doubt whether the squares and the cubes would be something you need to know in order to do a problem. But I just think everybody should know those. I don't know. That's also when it comes to algorithms, I might not necessarily ask you to memorize insertion sort, but if I ask you a question about insertion sort, I'll probably put the code on the midterm. But if you need to look at the code, you don't know it well enough. And when I say code, I mean pseudocode. You should forget about memorizing the pseudocode. You should memorize how insertion sort works. And then from that understanding of how it works, if you actually perform it on some blocks that you put numbers on and put them in front of you and do insertion sort, from that, hands-on, bare-knuckle understanding of how the algorithm actually works, from that you should be able to extract pseudocode. You should be able to get yourself to write down the pseudocode from that understanding. So, I usually do give the pseudocode for algorithms that I ask questions about, but with the idea in mind that if you need to look at the algorithm, you don't really know it well enough. But I will say specifically that Stirling's formula needs to be memorized. I'm not going to give you that for sure. Any other questions? Yes?
Do we also need to memorize the complexity formula?
Complexity formula of what? I mean, you do need to know the definitions of big O, big omega, theta, little o, little omega. Those definitions, those should be well understood. You should understand the theorems, all the limit theorems that I proved. I don't have in mind asking you to prove the limit theorems, but I do have in mind asking you to use the limit theorems. So they should be readily available to you, and I may or may not state them myself. I might, for all I know, I might ask you to state a definition. As a matter of fact, that's the very first problem here on the review sheet, is to state some definitions. I could ask you to state some theorems. So be able to use the limit theorems at the very least. Go ahead.
There was an equation for merge sort at the beginning of the quarter that was used to determine its runtime.
Yeah. Well, if you go to this problem is, I'm asking you to analyze an algorithm that is almost the same as merge sort, except it doesn't really do anything. It just does some mythical operation. And the analysis is basically identical to the analysis of merge sort. And the recurrence relation is very similar to the, so going from recursive algorithm to recurrence relation for T of n, is that what you're talking about, the recurrence relation for T of n? That should be something that you could emulate if you had to. Okay? Anything else? I don't see any other hands. Wave if I'm missing it. Okay, there you are. Go ahead. Louder, please.
Say we can use the result of a previous problem. Does that mean we can just use the notation?
No, the result, if you can use the result, results are always if-then statement. If this is true, then that is true. Consider that a wheel that's been invented that you don't need to reinvent. So if you can verify the hypotheses, you can extract the conclusion. You don't have to prove that the hypothesis implies the conclusion. See what I'm saying? But you do have to verify the hypotheses to use it. Go ahead.
Will there be solutions posted
for the midterm or for this? There are some, for the review sheet, there are some selected solutions that I will post, probably today or tomorrow maybe. Not all, but some. So, I mean, a lot of these are homework problems, and they'll be posted. For instance, this very first problem, the definitions. I don't need to post that. That's in the handout, right? So a lot of stuff doesn't need to be posted. So, but some will. Some will. Okay. Okay, that looks like there's nothing left. PA2 is closed, PA3 is open. I hope everybody had enough time to get some version of PA2 turned in, even if you didn't wring out all of your memory leaks and memory errors. The list that you built in PA2 in C is going to be used in both PA4 and PA5. So, it should be an ongoing task to make sure that you wring out all the bugs in that particular list. For PA3, you're going to kind of retool the list you made in PA1, right? The same list ADT, but in Java. So it's going to be, instead of a list of ends, it's going to be a list of objects. I hope everybody is, swimming in the sea of PA3, right? And you've gotten not just your feet wet, but your head wet. Okay? I don't know where that analogy came from, but and you got 2 weeks to do it, so maybe I'll wait till after the midterm before we start taking time on that, the time in class. All right, we got to get through some more stuff, so you'll be ready for the midterm. We're in the handout on induction proofs. And so that we've seen two versions of induction so far. The base case is to prove P of n naught. P is a propositional function of an integer variable, which means it's a statement that it involves some kind of integer parameter. The goal is to prove that that statement is true for all integers greater than or equal to n. So many versions of the induction step. 2a was this. Show that if for all n, show for all n greater than or equal to n naught, if P of n is true, then P of n plus 1 is true. And we introduced the domino analogy. This says that the n naughth domino falls. This says if any particular domino falls, then the next domino falls. Conclusion is for all n greater than or equal to n naught, P of n. All dominoes fall. Okay. I like this domino analogy, and I rely on it all the time to explain things. The reason I like it is it seems to me psychologically a very apt analogy, right? Because these two things occupy a certain related space in our intuition, I think. And the two things are physical cause and effect, one domino toppling another domino, and logical implication, one proposition logically implying another proposition. They're not the same thing, but I believe they occupy, or at least should occupy, a very close, a similar space in our intuition. If they don't, they should. Okay, here's another form of, here's the domino analogy, right? Here's the domino indexed n naught. There might be some initial dominoes that are not covered by the proof. They may or may not fall. We don't really care, but they're not part of the proof. At some point, there's the nth domino, then the n plus first domino, and there are infinitely many dominoes. We showed the first one falls, the one indexed n naught. If any particular domino falls, then the next one falls. Conclusion, they all must fall. Okay, that's 2a. 2b is a reparameterization of the induction step for all n strictly greater than n naught. You know what I mean by reparameterization? The parameter n has shifted, that's all. Instead of starting at, the induction still starts at n naught, but this statement, instead of starting at n naught, starts at n naught plus 1. Why? Because, what does it say? P of n minus 1 implies P of n. The reason we have to start that at n naught plus 1 is because we can't refer to any dominoes earlier than this one. But if we allowed n naught to equal n naught, this would be n naught plus 1, one of the dominoes that are not part of the proof. Okay, so that's why this strict inequality versus weak inequality has to be there. Furthermore, all it says is, for all dominoes, if any particular domino falls, then the next one falls. It says exactly the same thing as this one, except we're referring to, instead of the nth toppling the n plus first, it's the n plus first toppling the nth. All of this collectively is the first principle of mathematical induction, or weak induction. Okay, there's another form of induction called second principle, or also called strong induction. So, same base case. Also called second PMI. So the base case is the same, so I won't repeat it. And there are two forms of this second principle, just like there were two forms of the weak principle. And one was just a reparameterization of the other. Same thing is going on here. So, but this is a little bit more complicated looking induction step. For all n greater than or equal to n naught, if p of n naught is true and p of n naught plus 1 is true and all the way up to ... p of n are true, then p of n plus 1 is true. It's called strong induction because the so-called induction hypothesis, the thing you assume on the induction step, is stronger. I didn't bring up that term before, but what you assume to be true on the induction step is called the induction hypothesis. So in this case, this is the induction hypothesis. And in this case, we have a stronger induction hypothesis. Hence the term strong induction. We're assuming that more dominoes fell. So, in this case, what we need to show is for all n greater than or equal to n naught, if all dominoes up to and including the nth domino fall, then the very next domino must also fall. It's as if we need the weight of all of these preceding dominoes to topple the n plus first domino. Whereas in this case, all we needed was the weight of a single domino to topple the n plus first domino. Again, in an induction proof, we have to prove these things. We have to prove the base case. We have to let n be greater than or equal to n naught, choose an arbitrary n greater than or equal to n naught, assume the induction hypothesis is true, show as a consequence that p of n plus 1 is true. In this case, it's a slightly different formulation. We assume p of n minus 1 is true, try to show p of n follows as a consequence. In strong induction, we assume all dominoes up to and including the nth domino have fallen. Show as a consequence that the n plus first domino falls. Sometimes you'll see this written differently, such as for all k less than or equal to n, p of k. Well, that's just another way of writing this conjunction of statements. You know what that wedge means, right? That's logical and. Okay, so that's strong induction. It's as if we need the weight of all these dominoes to topple the n plus first. 2D is just a reparameterization of this in the same way that 2b is a reparameterization of 2a. So we show for all n strictly greater than n naught that if p of n naught and p of n naught plus 1 and all statements in between and up to p of n minus 1 are true, then p of n is true. So when proving this, we let n be greater than n naught. Assume all dominoes up to, but not including the nth domino, have fallen. Show as a consequence of that that the nth domino falls. All right, so that's what one of these two is our, the general form of our strong induction argument. Here is the induction hypothesis in this case. And in this case, you might see it rewritten in some texts, and maybe I'll say it this way sometime. For all k strictly less than n, p of k. Right? All dominoes up to, but not including the nth domino, have fallen. Okay. I have to do some examples. I wanted to just get all the the forms and the models of induction proofs out there first, because this is at least your second time through induction. So I'm not going to start from scratch. You've all heard of induction, done some induction proofs, and read some induction proofs. So it's okay for me to be a little bit abstract up front. At least I think it is. Now, before we go to an example, well, I can't think of what else I wanted to say. I wanted to say something else, but I've lost my train of thought. So let's look at an example. I'm sure I'll think of it. Let's look at an example of an induction proof. Something we're familiar with. One of those summation formulas. Here, let me fix this. Okay, example. Show that for all n greater than or equal to 1, the sum I equals 1 to n of I squared equals, I won't bother with the, power 1, we'll do the squared, equals n times n plus 1 times 2n plus 1 over 6. Okay, so first of all, what is P of n? P of n isn't the whole thing. P of n is the thing that this part of the statement that you're trying to prove for all n greater than or equal to something. So P of n is the boxed expression. Notice it's not a numerical function. People who write P of n equals that, the right-hand side, or P of n equals that, the left-hand side, are displaying their confusion, and therefore they lose points. Don't write things that aren't true. P of n is not a numerical function. It's not a number. It's true or false. So this is an assertion. The left-hand side equals the right-hand side. And the assertion, what we're trying to show is that this assertion is true no matter what n is, for all positive integers n. By the way, what is n naught in this case? N naught is 1 in this case, as it often will be. It's usually either 1 or 0, but not exclusively, all right? We should be prepared to begin the induction at any point. Okay, so how do we proceed? Well, 1, we have to prove P of 1 is true. Why? Why is P of 1 true? Well, let's write down P of 1. If that's P of n, P of 1 is obtained by replacing n everywhere you see it by a 1. I'm always shocked at just how hard this simple act of typographical substitution of one symbol for another, how that's so hard and so hard to conceive of. That's what the notation means. If that's P of n, P of 1 must be what you get when you replace n everywhere you see it by 1. So it's the assertion that the left-hand side of this, I equals 1 to 1 of I squared, equals 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Now, is that true? Well, it's just a fact of arithmetic. What's the left-hand side? 1 to 1, that's one term. It says 1 squared equals 1 times 2 times 3 over 6. In other words, it says 1 equals 1. Yes, that's true. We have verified that P of 1 is true. We have performed the base step. It is complete. Okay? And it's usually a trivial fact of arithmetic or something that follows immediately from the definition or definitions. Okay, let's proceed with 2a. This can be done with weak induction. Let's do the induction form 2a. Oh, I know what I was going to say before. Let me just talk about these 4 different forms of the induction step. 2a and 2b are all called weak induction. Okay. They are more or less, if you read induction proofs in a lot of books, and I have read a lot of them, I would say these are roughly half the time you see an induction proof written this way, half the time you see it written this way. That's why I want to bother to mention them both to you, so you're not confused by the difference, right? They're just 2 different ways of writing the same induction argument. What about 2c and 2d? I've found that when doing strong induction, 2c is very rare. I've seen it, but very few people who write proofs by induction, first of all, they're not going to be as wordy as me. They're going to be much more, they're assuming a lot more on the part of the reader than I will. But very few people parameterize their induction steps like 2c. It's maybe 1% of the time. So therefore, I'm not going to give you any examples of 2c when we get to strong induction, only 2d. Okay, but anyway, this is 2a. Here's 2a. So we have to show, let's write the script down. For all n greater than or equal to 1, because n naught is 1, P of n implies P of n plus 1. Okay, so we have to prove this. This is a universally quantified statement. Means that we have to prove that something is true for all n greater than or equal to 1. We have to prove essentially infinitely many statements. How do you do that? You have to choose an n greater than or equal to 1 and choose it arbitrarily. If you want to show that all horses are blue, you essentially have to show that hoarseness and blueness are the same thing, or hoarseness implies blueness. So it doesn't do any good to get a particular horse and say that horse is blue. You have to somehow say, let n be an arbitrarily chosen horse, and then deduce that it is blue somehow. All right, so the word arbitrary is important. So let n greater than or equal to 1 be chosen arbitrarily. That sentence is often left out by students because they don't think it's important, because they don't think the universal quantifier is important. It is all important. Remember, you're writing an essay and it has a certain form, and it won't compile if you don't write the right things in. For instance, you wouldn't dream of trying to write a Java program where you introduce a variable and you didn't declare it first. That's what you'd be doing if you didn't have this sentence. What is n? Okay. From now on in the proof, I can't use anything about n other than the fact that it is greater than or equal to 1. I can't use, if I implicitly use that it's even somewhere, then my proof is now invalid. Okay. So I choose an arbitrary n. Now anything I prove about n is true for all n. Now I have to prove this implication. How do I prove that? Assume the hypothesis. Assume P of n is true. It's not good enough for me, though, that you say that, because it's too abstract. I want you to say explicitly what you're assuming. When I talk about an explicit statement of the induction hypothesis, I want to see that, i.e., assume the sum I equals 1 to n of I squared equals n times n plus 1 times 2n plus 1 over 6. That's explicitly what we are assuming. Now, before I go any further, let me point out that some students reach a roadblock, a conceptual roadblock, right here. And what is the problem? They say, wait a second, you're trying to prove that formula, and you are now assuming that formula. But that's the very definition of circular reasoning, assuming somewhere in the proof the very conclusion you wish to prove, right? And therefore the proof is invalid, right? That's not, I mean, that's what a circular argument is. True enough, but that's not what we're doing here. I'm not trying to prove that box statement. I'm trying to prove that statement. For all n greater than or equal to 1, P of n is true. I'm not assuming that this formula is true for all n. I'm assuming that it is true for one n, the particular but arbitrarily chosen n greater than or equal to 1. That's all I'm assuming. I'm assuming that one particular but arbitrarily chosen domino has fallen. So sometimes I will say that for this n. Okay, just to alleviate that, that confusion. Now, what am I trying to prove as a consequence that P of n is true? I want to show that P of n plus 1 is true. We must show that P of n plus 1 is also true. Well, it's not good enough for me that you state it abstractly. I want to see it stated explicitly, i.e., must show that, okay, if that's P of n, then what's P of n plus 1? Replace n everywhere you see it by n plus 1. The sum I equals 1 to n plus 1 of I squared equals n plus 1 times n plus 1 times 2 times the quantity n plus 1 all over 6. So, on the assumption that the nth domino falls for an arbitrarily chosen n, I must show that the n plus first domino falls. Okay, so I require that you state this induction hypothesis explicitly in your proofs, and I require that you state this induction conclusion. Most people don't talk about the induction conclusion, but that's the thing at the other end of the arrow, right? Whatever's at the other end of the arrow. That's what I mean by the induction conclusion. The thing concluded on the induction step. State both of those things explicitly. Okay. All right, so we have a task before us. On the assumption that that is true, show that that formula is true. Okay. So, let's do it. Well, there's nothing, we've kind of, I think of induction as a machine, and we've turned the crank on this machine, and there's only so far you can go with that. At some point, you have to actually use, what you know about mathematics. All right, now's the time. Let's start with the left-hand side and reach the right-hand side. Along the way, we will use that assumption. The sum, I equals 1 to n plus 1 of I squared equals, what am I supposed to do with that? I have an assumption that involves the sum I equals 1 to n, but that's part of this sum, isn't it? That's the first n terms of this sum. It's a good idea to peel off the last term, I equals 1 to n of I squared, plus the term I left out, which is what? Somebody tell me. N plus 1 squared. Right? This is just nothing but the meaning of the summation notation. Right? Leave off the last term and write it manually. Now this expression in parentheses is the left-hand side of the induction hypothesis, which was assumed to be true. Therefore, I may replace it by the right-hand side. So this is equal to n times n plus 1 times 2n plus 1 all over 6 plus n plus 1 squared. And why is this? This is true by the induction hypothesis. That's one more thing that I require of everybody to get full credit on an induction proof. State the point or points in the proof at which the induction hypothesis is being used. After all, if you're writing a proof and you're not using the induction hypothesis, do you really need an induction proof? If it's correct, you don't need to be doing it by induction. Okay, the rest is just algebra. Algebra on this to reach that. I guess I could just leave that as a exercise, but let's go ahead and do it. 5. So this is equal to, well, you might think square that, multiply that out, but then you're just going to have to factor later. So let's write this as n times n plus 1 times 2n plus 1 plus 6n plus 1 squared all over 6. I put the two terms over a common denominator. Now factor out n plus 1. n plus 1 times n times 2n plus 1 plus 6 times n plus 1, right? Instead of multiplying out, factor, because you want a factored form anyway. But I'm trying to get to a factored form. So this is equal to n plus 1 times 2n squared plus n plus 6n plus 6 over, oops, forgot the 6. That's equal to n plus 1 times 2n squared plus, looks like 7n plus 6 all over 6. And if I factor that, you notice we get n plus 1 times n times 2n. And it turns out to be n plus 2, I believe, 2n plus 3. Let's check. 2n squared, 4n plus 3n is 7n, 2 times 3 is 6, okay? Over 6. And that turns out to be exactly what we have here, which is n plus 1. I won't usually bother to write it this way. I mean, the equivalence of that and this I would normally take to be obvious, but I'll write it this time. N plus 1 times 2n plus 1 all over 6. Now, at this point, I should just wrap up the proof, because I've completed the induction step. Now let's state the conclusion. By the first PMI, the sum I squared n times n plus 1 times 2n plus 1 all over 6 holds for all n greater than or equal to 1. Now, sometimes I'll be lazy and I won't write that last sentence, but you should say, we're done somehow. Question? What do you mean the opposite direction? From this to this? Algebraically? Well, I would say it's often, yeah, like what algebraic steps, it's not often clear what algebraic steps I would have to take to get from this expression to this expression. And it might be sensible to kind of work from this point to this point, or maybe work from both these points to some common point in the middle, right? However, that's not the way you write your proof. Remember, proofs are written in the forward logical direction. So that's your scratch paper. That's the proof discovery that you're talking about, right? Discover the proof by working backwards from this expression to this expression, or at some common point in the middle. Okay. All right, so that's our first induction proof. Any other questions on it? There are going to be a lot more. Here's another one. I'm going to do another weak induction. So, let x be a real number, x not equal to 1. Then for all n greater than or equal to 0, the sum I equals 0 to n of x to the power I is equal to x to the n plus 1, sorry, yeah, that's right, x to the n plus 1 minus 1 over x minus 1. Okay. Notice there's this other parameter. There's an invisible universal quantifier in front of x for all real numbers x, not 1. I don't bother to put it because that's not part of the proof. You might as well think of x as fixed throughout the proof, as long as it's not 1. Anybody recognize this? This is the sum of the nth partial sum of a geometric series, right? Where the coefficient is just 1. You saw that in a calculus class. All right, so what's P of n? Again, P of n is the boxed statement. That's P of n. What's n naught in this case? N naught is 0, because we're starting the induction at n naught. So here's the base case. P of n naught, P of 0 says what? We have to check that P of 0 is a true sentence. The sum I equals 0 to 0 of x to the power I equals x to the power 0 plus 1 minus 1 over x minus 1. In other words, it says, since there's only one term, x to the 0 equals x minus 1 over x minus 1. But both sides are just 1. 1 equals 1. That's true. So P of 0 is true. And the base case is satisfied. Okay. Now, we did 2a last time. Let's do 2c, just so that we see something different. 2b, yeah, not 2c, 2b. Thank you. 2b. What was the script? I think of this as a script, or kind of like a Yeah, here's what it said. For all n greater than n naught, which is 0, p of n minus 1 implies p of n. That's what we aim to show. I think of this as kind of like a legal form. You know, if you want to, like a do-it-yourself, you know, rental agreement or a do-it-yourself divorce or something like that, what do? Some people might have that problem. So you actually, you could download. There's an online company, I think, that does this. What's it called? LegalZoom. You just contact them and you pay them some money and you download the forms and then you fill them, use their instructions and you fill them out. And then you have something with the force of law, I guess. I don't know. That's kind of what this is. This is a legal form and we have to follow the script. And if we don't, then it doesn't have the force of law, right? So the first thing we have to say is let n greater than 0 be arbitrary. After a while, I'll get tired and I'll just say, let n greater than 0. That's good enough, okay? Assume for this n, not all n, but just this n, that p of n minus 1 is true. Okay, let's write down the induction hypothesis explicitly. P of n minus 1. Replace n by n minus 1. So it would say the sum I equals 0 to n minus 1, x to the I equals x to the n minus 1 plus 1, that's x to the n, minus 1 over x minus 1. We must show P of n is true. That's what this says. Induction conclusion. In other words, the sum I equals 0 to n, x to the I equals x to the n plus 1 minus 1 over x minus 1. So from the assumption that the n minus first domino has fallen, n is arbitrarily chosen, we must show that the nth domino falls. Okay? So, well, again, I've turned the crank, I've filled in all the forms, I've got to, I don't know, maybe this is where I serve the writ or something like that. I don't know, this analogy isn't really working, but, because I don't know anything about the law, but, you know, I like thinking in analogies. It helps to think in analogies and metaphor. So let's start with the left-hand side. I equals 0 to n of x to the I equals, well, what did I do last time? I wish I had a statement that was like the induction hypothesis, that had the sum going to n minus 1. Well, that's contained in this sum. So this is the sum I equals 0 to n minus 1 of x to the power I, plus the one term I left off, which is x to what power? Not fast enough, guys. X to the n. X to the n. Right, so this is nothing but the same thing written slightly differently. Okay, but now the thing in parentheses is the left-hand side of the induction hypothesis, which was assumed to be true, and therefore I may replace it by the right-hand side. So therefore, this is equal to x to the, let's pull it down, I hope you can see it all, x to the power n minus 1 all over x minus 1. That's what's in parentheses, plus this term x to the n. Okay. Now it's just algebra to try to reach that right-hand side. Okay, so what do? X to the n minus 1 plus x to the n times x minus 1 all over x minus 1, which is x to the n minus 1 plus x to the n plus 1 minus x to the n all over x minus 1. Am I making a mistake somewhere? No? Okay, I'm just hearing people talk, that's all. As long as it's not my phone, I don't really care. I mean, I care, but I'm not embarrassed if it's not my phone. Okay, so this is x to the n plus 1 minus 1 over x minus 1, which is what we wanted. And done by, first, PMI.
Do we have to state the PMI that we're using? I get why you do it.
Yeah. Will you lose points if you don't? No, you won't. But I do need to know which version of PMI you're using. So if you think there's any possibility for confusion, you should tell me. Because if I have to guess, then you're going to lose points. I mean, there's lots of ways that you can start to confuse the grader. And you don't want to do that. Okay, well, so far we've done 2 weak inductions. Most of the inductions in this class are going to be strong inductions. So let's get to one of those. Also, the 2 things we just proved were 2 summation formulas. You probably did a lot of that. You probably did these 2 examples in your CE16 class, right? I would hope so, right? Unfortunately, many beginning students get the idea that induction is a method for proving summation formulas. It's nothing of the kind. All of these summation formulas have much more creative and more inspired proofs that are not induction proofs. And you probably saw some of them in CE16, some of those non-induction proofs with the same summation formulas. But just let me leave you as an exercise. Use both 2a and 2b. So it's 2 problems, but it's actually 4 problems. I want you to do it once in the form 2a, once in the form 2b. The cubes. Oh yeah, sorry. For all n greater than or equal to 1, sum I equals 1 to n of I cubed is equal to n times n plus 1 over 2, the quantity squared. And for all n greater than or equal to 1, how about 4th powers? I wouldn't expect anybody to have memorized this. That's going to be a 3rd degree polynomial, a 5th degree polynomial. N times n plus 1 times 2n plus 1 times 3n squared plus 3n minus 1 all over something god-awful, 30. Okay? So this one is just, they're all equally challenging. It's just that it's a little bit more messy algebraically to do these last 2. But put them in both forms, 2a and 2b. Okay. That's weak induction. Let's look at some examples of strong induction. This is example 3 in the handout that I'm up to. Page 3 of the handout, example 3. So, define T of n for n greater than or equal to 1 by the following recurrence relation. This is a little bit more up our alley, isn't it? What we're doing in this class. T of n is 0, T of floor n over 2 plus 1. This is in the case n equals 1, in the case n greater than or equal to 2. What algorithm does that recurrence relation remind you of? What is that giving you the runtime of? Say again? It's binary search, right? That's nothing but binary search. You see, I really want you to try to, identify the recurrence relations and what recursive algorithms they go with. This is nothing but binary search, because what does it do? It takes the search space and cuts it in approximately half each time. And what's the 1? The 1 is the cost of the three-way comparison. Did we hit the target? Is it less than the target? Is it greater than the target? And we're assuming worst case here, so we never hit the target. So we have to do one more comparison. So the cost of doing all that three-way comparison, is the basic operation, 1. Okay, what are we supposed to prove about this? Prove for all n greater than or equal to 1, t of n is less than or equal to log base 2 of n. And by the way, what does this show? And hence, proving this inequality for n greater than or equal to something, anything, shows that t of n is big O of log n. Notice when I write the asymptotic expression, I don't bother to mention the base of the log. Okay, but the inequality holds for log base 2. All right, so let us proceed. This is going to be strong induction. The base case is the same either way. And by the way, what is P of n? P of n is not a summation formula, it's an inequality. That's P of n. So, what is n naught? 1. So, P of 1 says that t of 1 is less than or equal to log base 2 of 1, right? i.e., t of 1 is defined to be 0. Log base anything of 1 is 0. And that's a true statement. Okay, base case, a triviality. Now let's go to induction form 2D. We're skipping C, remember, because it's very unusual. Okay, so (2D). Well, let's write down. Let's print out the legal form. All right. Well, let's write the script. It says, for all n greater than 0, if p of 0 and p of 1 and all the way up to p of n minus 1 are all true, then p of n is true. This is the so-called strong induction hypothesis. I show that for an arbitrary n, if all dominoes up to but not including the nth domino fall, then the nth domino falls. All right, let's deal with that for all. Let n greater than 0 be arbitrary. Now, anything I prove about n holds for all positive n. Oops, did I miss something here? Oops. Yeah, n naught is 1, not 0. I know, I got mixed up by that 0. That should be 1. Sorry. Right, I got mixed up by that 0, but the fact is this is supposed to be true for all n greater than or equal to 1. N naught is 1, and that's what I should have had there. Where did I do it wrong? I don't have P of 0 in, oh yeah, you're right. That's right. P of 1 through P of n minus 1. Don't worry, I'll erase that and make it look like it never happened when I post the notes. In fact, I have an even better idea. There, that's K2. D. We're supposed to show that for all n greater than, don't let me see you do that on an exam. P of 1 and P of 2 and P of n minus 1 implies P of n. So let n greater than 1 be arbitrary. Now, how do I say that in words? We need to say that explicitly. Another way to say this is for all k in the range 1 up to but not including n, P of k. I bring in another parameter. It's another way to say it. Assume for all k in the range 1 less than or equal to k strictly less than n, that P of k is true. In other words, T of k is less than or equal to log base 2 of k. I'm assuming that T of k is less than or equal to log k for all k in the range 1 up to but not including n. That's the assumption that all dominoes up to but not including the nth domino have fallen. What must we prove? We must show that P of n is true. In other words, that formula is true for this particular n. T of n is less than or equal to log base 2 of n. Okay? Now, somehow I've got to get from this left-hand side of this inequality up to the right-hand side. Along the way, I get to use that this was true everywhere along the way. Now, let's look at the recurrence for a minute. I've assumed a lot here. I've got a lot of dominoes falling down, but there's only one domino that I really need. It's not the domino immediately preceding the nth domino. That's why this can't be weak induction. But it is somewhere, a specific domino, some part of the way back from the nth domino. Which one is it? What is its indexed? Say again? No, it is not n minus 1. Look at the recurrence. It is, say again? Floor n over 2. So, of all the dominoes that are assumed to be falling, the one that we really care about is the one indexed floor n over 2. All right, so let's begin. Start with the left-hand side and get a chain of inequalities that works up to the right-hand side. Now, T of n is equal to T of floor n over 2 plus 1. I mean, we've got to use the recurrence somewhere in this proof. Otherwise, what does this apply to? Only to this function. This is by the recurrence formula. Okay, so this is, the induction hypothesis says that if k is in this range, then T of k is less than or equal to log base 2 of k. But floor n over 2 is a number in this range, is it not? So therefore, this term is less than or equal to log base 2 of floor n over 2. Why? This is by, plus 1, sorry, the 1 goes along for the ride. By induction hypothesis, with a particular k equaling floor n over 2. Okay? So this is just one of the dominoes. One of the preceding dominoes is the one that's being used here. Now this is less than or equal to log base 2 of n over 2 without the floor plus 1. Why is that? Because floor x is always less than or equal to x. And log is an increasing function. You put something bigger in it, you get something bigger out. Laws of logarithms. This is equal to log base 2 of n minus log base 2 of 2 plus 1, right? But what's log base 2 of 2? So that's a negative 1 and that's a positive 1, and they cancel, and I get log base 2 of n. And so therefore, no. What's on the left-hand side of this equals sign? Don't get mixed up, guys. It is not this. T of n is not equal to this. The left-hand side of that is sitting right above it. It's not T of n. It's a chain of inequalities and one or two equalities sprinkled in. Okay, so therefore, T of n is less than or equal to log n for all n greater than or equal to 1 by second principle of mathematical induction. Okay, so before we end, let me just point out what makes strong induction necessary in this case. You can only use weak induction if the domino that will topple the nth domino is the immediately preceding one. N implies n plus 1 in case 2a, or n minus 1 implies n in case 2b. However, if any other domino, or any combination of dominoes, or some random selection of dominoes are needed to topple the nth domino, you have to go with strong induction. So that's how you know when strong induction is needed. Always ask yourself, which domino is going to topple my nth domino? Okay, I will see you Wednesday. We'll do more of these examples, and hopefully you're going to be prepared for all the problems on the midterm review sheet, and therefore the midterm. Don't forget, homework is due on Wednesday also. Go ahead.